Morning, everybody. I'm Steve Wachowski. I am from Moat up in the Buffalo area. I am also your honorary co-chair of this event, and I'm here to talk a little bit about AAS. Just as maybe a show of hands, how many folks out here are members of AAS? Okay, so those who are not, look around, okay? How many of your companies are actually corporate members? Okay, not a super lot of you. So this is going to help. Chris talked about networking a little bit up here. I thought that was great, and that's one of the great things you get by being part of the American Astronautical Society. Jimmy Kenyon the other day had brought up so what are you doing to help the cause? We as the American Astronautical Society are actually out there to help promote all things space, if you will. We're actually run by a pretty small staff. Jim Way over here, Marta, Emily, and Jules are the actual paid staff members of the society, but the remainder of that society is actually the membership. Okay, as a member, you get copies of 6 times a year. We provide a journal out there. We also have these multiple different events that you can come to as a member. You always have a reduced rate on that. But I think that most important thing, again, is that ability to network. So I've been on the board here at AAS for, wow, too long of a time, probably. But it's been a really great experience. And what it's really helped with is actually being involved with a super group of board members out there. But it's also, before I became a board member, I started getting involved in different things, being involved in setting up these type of events. As members, we look to have our teammates come in and actually help to produce what is going to be on for each one of these different events, and that diversity of think is great for providing that. So I'm going to ask our next team to come up, our next panelist team to start coming up, and I will finish my talk so they can jump right into theirs. So again, we have multiple different technical committees that also put on events for us throughout. But any of you who would like to get a little bit more involved, I would say just reach out to a board member, reach out to Jim Way, who's up here. You can send an email off to aas@astronautical.org to get a little bit more information and get yourself more involved in the group here. So I'm going to move us right on to our next panel of guests here. I had an opportunity last week to talk with them a little bit. They're going to talk about the technology of radioisotope, power systems. They're super group of folks. They are really knowledgeable on all things in that. And I think Jim's going to start us off here. So Jim, get us rolling.
Sure. Thanks for having us. I just want to take moderator's privilege for 30 seconds and retroactively plug the tech transfer panel, which did an awesome job. One of the groups that reported to me when I was the Deputy Chief Technology Officer at NASA was tech transfer. And the most compelling reason that NASA should be involved in tech transfer, aside from the fact that it was written in the very first Space Act in 1957, is that this technology belongs to the American people. And so if you see something that resonates with you, always contact the tech transfer offices because it's yours, and they'll help you find a way to turn it into something fantastic. So anyway, that being said, I retired in 2016. And the job I had before the deputy chief technologist job was I was in planetary science working for Dr. Jim Green. I became the advocate at headquarters on what are we going to do about the lack of plutonium-238, which seems like kind of a niche topic, but it's crucial, and that's what we're here to talk about today. So we've assembled this panel. We're here for a reason, and it has to do with the budget situation, right? Well, everybody's worried about the budget, but we're worried about this one niche topic. And so we've got Ralph McNutt from Johns Hopkins University Applied Physics Lab. We've got Dr. Jim Green, former NASA chief scientist. We've got June Zakrajek, who is now with the Aerospace Corporation, but when I knew her, she was running the RPS program office here at Glenn. And what we're going to do is we're each going to take 5 to 10 minutes in not this order, so I'm not talking first, and set the stage for comments. And then we just want to have a Q&A session. So we'll give you an idea of what the background is and why you should care, and then we'll have a Q&A. So the first up is Dr. Ralph McNutt, who's been involved in radioisotope power and nuclear systems since, well, I think Moses was still wandering in the wilderness, right?
Or a little before that.
Yeah, well, right.
Thank you, Jim. All right. Well, what I want to do is to give you a little bit of a background on this, because this has been something that's been a long time in the making. And all right, which one of these goes forward? The big one. Thank you. And it's I'm gonna just flash through a lot of view graphs. Sorry about that, but hopefully we can get these posted out there for you guys at some place as well to go back if you want to look at for reference. So this is really a story. Big one, huh?
Maybe next slide.
There we go. So the story actually goes back 80 years. Really, the origin of all this was with the end of World War II and the beginning of the Cold War. There was a mission need at the beginning of the Cold War in 1952 for having a 500-watt electric power supply for a satellite. It was called the Space Nuclear Auxiliary Power Program. It was highly classified at the time. It was an assignment that went to the Atomic Energy Commission and was based upon Project Feedback, that was a classified at that time study by the RAND Corporation for being able to do satellite surveillance of the Soviet Union. We had parts that had actually been proven during World War II, including something called the polonium-210 initiators, which were used in the implosion-type device atomic bombs. The first one, of course, was tested at the Trinity site in July of 1945. The origin was with that polonium-210 fuel because it gave us a way of being able to produce a supply of alpha particles. And that was investigated actually at the Mound facility in Miamisburg, Ohio. That started back in 1948. And of course, that site was eventually moved because of considerations about safety and security from the 9/11 attacks. But suffice it to say that there were RTGs, radioisotope thermoelectric generators, that were powered by polonium-210 that were invented at Mound. And this was, again, this was all the pieces that you needed for actually making a power supply. So the RPS program, all in all, this is an enabling technology for providing power and heat to satellite systems. Again, the invention came out of some of the work that was done at Mound. It was about $4.7 billion that had been invested by FY 2011. I did a quick calculation this morning. That amounts to about $7 billion in current year dollars. This is a lot of money that went into this. Right now, all of the infrastructure and production are financially supported by NASA's Planetary Science Division. Back in the day before then, there were other customers within the U.S. government that were bearing most of the development cost. The use in satellites has always been enabling. We found that out with the with the Starfish test. It was a hydrogen bomb detonation over Johnson Atoll in 1962, which basically blew a lot of satellites offline because at the time, the satellite solar arrays could not deal with high radiation levels. First actual use was in the Transit 4A satellite, the precursor to the Global Positioning System, 2.7 watts of electricity powered by plutonium-238. That was flown in 1961. And again, plutonium-238 was the isotope of choice. The initial research was transferred to Mound from Lawrence Livermore in '59, and Mound actually produced well over 500 units powered by this isotope. There are other isotopes people have looked at. They were looked at beginning in 1947. We've kept going around and around, taking a look at these over and over again, and I'm not going to go into the details, but suffice it to say, the best identified has been plutonium-238, and that's what's been used in all of the units that have actually flown on satellites. There's been the use of strontium-90 in various terrestrial units, some by the U.S. Navy along the way. Americium-241 is something that's been noted more recently about perhaps being used. We've looked at that and looked at that. I actually co-chaired the National Academies panel in 2008, 2009, looking at plutonium-238 and the use in RTGs for NASA. We had a lot of good discussions with the Department of Energy at the time and took a look at americium-241 at the time. It makes no sense for the U.S. It's not the best choice, but nonetheless, there have been investigations into using it. Of course, you may have heard of it from being used in smoke detectors, which has been used for a long time. About 24 micrograms per smoke detector. Not a lot of material, not in the kilogram range that's needed for these kind of instruments. There is a continuing European effort that's being funded at the moment for about trying to get use that radioisotope for the European Space Agency. That's an ongoing effort and hasn't gotten to a unit yet. They're still doing development. What I think people don't realize is that the production and separation of plutonium-238 were carried out at Savannah River in South Carolina. This was an industrial scale facility used for Ulysses and Galileo radioisotope power supplies. The H Canyon was a building that was built in order to actually produce plutonium-238 and its precursor neptunium-237. This is a building over 1,000 feet long, 100 feet wide, 71 feet tall, 6-inch thick concrete walls. It was hardened against nuclear blast. It is still being used. It's one of the 6 canyons that were built for doing processing for the weapons part of the United States developments, going back to Hanford and Washington. It is still being used. There is a hot side and there is a warm side. The hot side has not had a human being inside since 1956 when it went online. It is still being used now for doing various things with fission power supplies and radioisotope fuel. The new plutonium-238 supply project for NASA is more modest. We were looking at producing about 1.5 kilograms per year plutonium-238, starting in either in FY26 is the plan. Again, to be able to put into satellites. We've optimized the packaging over the years for safety, reliability, and cost. They're complicated encasements of the fuel in order to make sure that we can check all of those boxes off. In the multi-mission radioisotope power systems, these were originally conceived of in 2001 as the backup supply for when we were starting to look at dynamic converters. Dynamic converters have had a lot of promise. They've had a lot of work that have been put into them, but we're still not there yet for an operational system. We have built 4 of the MMRTGs. Flight Unit 1 is on Mars working now on Curiosity. Flight Unit 2 is on Mars working now on Perseverance. There's a Flight Unit 3 that's unfueled at Idaho National Laboratories that can be used for a future mission. And Flight Unit 4 is in fabrication for the Dragonfly mission that will be going to Saturn's moon Titan. And one final note, and I've forgotten about this slide. Just wanted to remind everybody that the future of space exploration is up to us now. And as was remarked earlier, there is a big issue with the budget coming up. These have been enabling supplies. It will enable us to do things in the future that there just simply is no other way to do.
And keying on that is Dr. Jim Green.
Thanks very much. All right. In 2006, Jim Adams and I ended up the process of managing the planetary science, I as the director and Jim as indeed the deputy. And things were pretty good. Department of Energy had been supplying us plutonium-238. They had a supply left over from the bombs program, as Ralph has talked about. In addition to that, we were buying plutonium-238 from the Russians. But a few years after Jim and I were in planetary, in 2009, the Russians decided to stop selling plutonium to Department of Energy and therefore for NASA's use. And this caused quite a dilemma. And the reason why is we had a very small supply. It was very dwindling for each and every mission that we were doing. And we had upcoming missions. These classes of missions, the large ones we call flagships. These are like Cassini, Curiosity, Perseverance, and we also had New Frontiers missions that were also being solicited, and some of those actually had radioisotope power requirements. Here's an example of the New Frontiers program that we faced. Jim and I came in, Juno was just selected, and we were in the process of building it. And indeed, New Frontiers 3 out of the list of 5 or 6 missions, each of these missions required radioisotope power capability. It turns out New Frontiers 3 that was selected was OSIRIS-REx, which was a asteroid sample return, which actually has completed its primary mission. The samples are in the laboratory being studied, and fantastic things are coming out of it. And that's what we want the New Frontiers program to do. But any one of these could have been selected at the time. Now, the community started being alarmed about the lack of plutonium production. Because we weren't buying any more from the Russians, we weren't getting any more in our supply. It was constantly being reduced. And so Jim in particular as my deputy, I tasked him with, let's try to fix that. That turned out to be very non-trivial. To be able to get new money from Congress, the stars have to align. So you've got to get the administrator on board with that idea. You've got to get OMB on board with that idea. You've got to get OSTP and the administration's approval to do this before you can even get it to Congress. Well, it turns out we worked very hard on that. Jim in particular did. And by 2011, the stars did align, and we were given the opportunity to then work with the Department of Energy to figure out how to move forward with plutonium production without making a bomb. All right? So this is all nuclear physics, all new things had to be created. And they did. They did a fabulous job, came up with the way to do that, which turns out to be irradiating neptunium, which we do have a large amount of neptunium with neutrons in the reactors, for which then we can cull out in that reaction plutonium-238. We also had a schedule that we put together based on the ever-increasing use of their existing facilities. And that was by 2019, FY 2019, we did 400 grams per year. By 21, we put a Department of Defense or Energy put on new facilities. And by 2025, we'd start up ramping up the production to 1.5 kilograms, with other thoughts of increasing that supply later, if needed. So here's a wonderful graphic that I've always did enjoy. This is actually, it was created in 2017 as we were talking to the community. It folds in what our existing supply was. So we had existing plutonium-238 that could be used, that is in spec with our abilities, was only 17 kilograms. All right. We also had additional plutonium, which was much older, and of course, not in spec, would not be able to produce a maximum power as we needed. Had already decayed over time, of course. But now the new production can come in once again, starting in 2019 and ramping up over time, enabling us then to cull out of that our new missions, new MMRTGs, new radioisotope power systems that would be able to handle future requirements. Well, I'm here to tell you there are a lot of future requirements. The first one, as Ralph already mentioned, Dragonfly. The MMRTG system that houses the plutonium that generates the heat and therefore charges the battery and runs the instruments. That's being put together right now, and that's going to use 4.8 kilograms out of that supply right away. In addition to that, the planetary decadal has come out with a whole slew of missions. And what we see in each of these opportunities in the next new frontiers area, they're largely RPS systems. All right. Depending on the proposals and what comes in, there are a couple like going to Ceres. Can we get away with solar or not? Not quite sure. Or things like going to Venus, but certainly if you're going to go down to the surface, you're going to have some long-lasting power. And so there are some things that may not require it, but there are more that do than don't. So this is indeed now the case. We've turned that around. The community used to say, well, that if we don't end up with plutonium, that means to us the outer solar system is off limits. There's just no way we're going to be able to do the things that we need to. So this has really been a tremendous advantage for us because of our future program. We've studied the inner part of the solar system really well because we can. And now radioisotope power capability, as we have created the opportunity to continue to make, gives us a way to the future. And of course, with super heavy lift launch vehicles, whether it's the SLS or Starship or many of the others that are coming online, that allows us to get out there much more quickly, and even well beyond the heliosphere, out in the winds where other stars are, where the Voyagers are today. The top flagship for planetary science is a mission to Uranus. Once again, can't go to Uranus without radioisotope power. So this has really provided us a wonderful opportunity to keep the community going and keep making the fabulous discoveries that radioisotope power capability enables. Right? Next one, June.
Yeah, so I'm next. So if we could bring up my slides, that'd be great. Maybe I just hit this button. Huh? No, that's too far. There we go. Yeah. So I have just 6 slides, and they're mostly thought provokers, right, based upon what Ralph and Jim have said. And then June is the anchor presenter, and I think she's going to be even more provoking. So the backgrounds on my slides really don't have anything to do with the words on my slides. They are images from missions that have been RPS, radioisotope power system, enabled. And this is Cassini at Enceladus. So why should we be worried about the production of plutonium-238? Well, for one thing, the president's passed back budget to NASA cuts outer planetary exploration and cuts off the production of plutonium-238, which by fiat cuts off outer planetary exploration. And it doesn't matter if we're going from in close to the darkish side of Mercury or all the way out to Pluto and the Kuiper Belt. Plutonium-238 is needed to produce power. As Ralph has pointed out, U.S. leadership has paved the way for this science. It is the United States technology and the United States science that has led the world in understanding our entire solar system. It could not be done without radioisotope power systems and plutonium-238. I also have a whine on there that if we cede that position now, we're going to regret it in the future. The alternatives to date are undeveloped, lower efficiency, and hazardous. And as Ralph has pointed out, we've been studying this for 70 years. We've been investing in plutonium-238 radioisotope power systems for 70 years. And to jump to a different isotope or a different system without fully exploring its uses and its necessity is a mistake. It's like changing horses midstream when the horse isn't there. And so I would caution people when they hear about americium-241 to start asking the hard questions. Well, where is the supply going to come from? How is the Department of Energy going to regulate that? What does that mean for the systems that it would interface with, right? And how, and basic systems engineering questions. What kind of power would it put out? How much is it going to weigh? You know, how hard is it going to be able to get? And I think it'll be very enlightening that we are today not as far along with alternate radioisotopes as some in industry would have us think. Let's see. We also need to continue the technology development that goes along with radioisotope power systems. The GPHS RTG, which powered Voyager and Cassini, utilized something called silicon germanium unicouples. Today we don't have that recipe anymore, and it's time to bring them back. Why? Because they last longer than the kinds of thermocouples that we are using in the MMRTG. And so we invest in that technology, go back and begin to, again, to continue the investment in things like Stirling and Brayton cycle engines that are far more efficient than the passive RTGs. There's a huge debate in the community about would I rather have a passive system that is 8% efficient, so I put 100 watts of heat in, I get 8 watts out, or would I rather have a mechanical system that has to operate for these missions, like it took us 9 years just to get to Pluto, right? It has to operate in deep space for 9 years without missing a heartbeat. So that mechanical system becomes a risk, but it also produces on the order of 28%. So you put 100 watts in and you get 28 watts out instead of 8 watts. So there's a place for dynamic power systems, and there's a place for silicon germanium converters. This is something I felt like from the very beginning, is that we need to look at higher power RTGs again. The GPHS RTG used to put out about 300 watts. Today, the MMRTG is at 120 watts, right? Now, what's happened since the days of Cassini is we've figured out how to run missions on much lower power, right? The power of Juno, which isn't RPS powered, by the way, at Jupiter is less than 500 watts, right? But still, we need a higher power RTG to power anything that would go deeper beyond Jupiter. A little bit of competition is good too, you know. So we had trouble with RTGs and plutonium supply, and so the community, especially the tech community here at Glenn, stepped up and they figured out how we could fly solar arrays, not out to Mars, but all the way out to Jupiter. But I can tell you, going out to Saturn would be nearly technologically impossible, right? Now I say that and come back in 20 years and we'll probably be flying solar arrays out to Neptune. No. All right. Anyway, So that's where I'm at with my technologist hat on. There's still room to grow in this technology, and I think that we need to capitalize on that. If you haven't gotten the message yet, Ralph said it at the outset, Jim has said it, I'm saying it, MMRTG, plutonium-238, that's the proven capability, that's the state of the art right now. By the way, I know that in this picture, that's not a MMRTG, that's a snap, right? But the capability that we have today is MMRTG and plutonium-238, and if we're going to grow into some other system, we need to do it in a logical and informed manner rather than cutting one thing off and hoping that the technology will be developed in time for the next mission. This is sort of, I mentioned this to Rads the other day. What the U.S. needs is a long-term policy on exploration technology infrastructure. Because when you start something and then have to terminate it or slow it down because of politics or budget, you impact everything that happens downstream. It's not a thing that you can buy back next year. And so that's sort of my whining point and getting off the stage point is we need a long-term strategy, not just on RPS, but on many other enabling technologies and U.S. infrastructure if we're going to keep our preeminent place in space exploration around the world. And somebody once said to me, the U.S. must decide if we're in this for the long haul or not at all. So with that, that's my last slide. And now we've got June to sort of wrap it all up, and then we'll do Q&A.
All right. So our last panel said something about falling in love with the problem. And so I'm going to start there because I retired and I thought that was going to be it. But I didn't, because I fell in love with this idea of the exploration and how RPS helps us explore. So sitting here today, my husband's probably not as happy that I fell in love with RPS as I did, but I'm sitting here today because of that, right? So right now, 12 billion billion and 15 billion miles from here are two spacecraft, right? We've got Voyager 1 and Voyager 2. They took a tour of our solar system and they uncovered things we had no idea about, and they're still sending back science. And they're doing that because we have RPS. If we didn't have RPS, they would not be able to do this. Let me go to the next chart. I only have one chart, really. There we go. This shows you all of the missions we have done and how we've explored in the last 64 years because we have RPS. This is nothing new that you haven't heard before, all right, from the panelist here, right? But it really does see that you can explore by flying by, you can land, you can rove, and pretty soon in 28, we've heard about the Dragonfly mission. We'll have a Dragonfly mission that goes to Titan. And it really will, it's going to break a barrier for exploration for us, right? All of our landers or rovers to date have only been able to rove around where they landed. We're going to rove over 70 miles on Titan, a planet that has not a water cycle, but something similar, a methane cycle. It'd be so cool to find this out. That mission is unexecutable if you didn't have RPS, all right? And so we heard in 1988, we shut down the production of plutonium here in the country. And it took us decades to get people aligned to restarting it. And in 2015, DOE rolled off the first few grams of that product. Those are on Perseverance right now exploring Mars. We showed end-to-end in 2015 that ability. Now, the DOE also said at the time that they weren't going to, if we shut this down again, they're doubtful that we'll ever be able to bring it back. Why? They were able to still get into some facilities that were existing, all right? Our plutonium production takes 3 of the national labs now to put in place. And so I kind of feel like we lost something, we found it, and now we have a hole in our pocket, and we're about ready to lose it again if we don't change the budget. And so we need to do that. And that 1.5 kilograms per year that we said that we needed, that everything will be in place within the Department of Energy by the end of 2025. So we're going to have everything in place, and then once we finish Dragonfly, we're going to shut everything down. And this isn't like shutting down an Amazon warehouse. We're not going to be able to just shut the door, turn off the lights, and walk away. These are nuclear facilities. They're going to take time and money to shut them down safely. Potentially more money than it takes for us to run them to produce plutonium so that we can explore deep space. So, and so I'm afraid that if we do this and we go down this, we will lose this for good. And we won't be able to explore the outer planets. We will not be able to compete with China on the moon. Right now, China has spacecraft on the lunar surface that have radioisotope power systems on them. But the United States does not, because we're still making decisions on how we're going to explore. As you saw in, I think it was Jim's slide, Adam's slide, you saw you can use these systems around humans. We've done it before. They are able to be used around the astronauts. And so we can't take the chance of losing this capability, this precious capability. Now, we've heard about alternative isotope systems, and they are on the horizon. And ESA, working through the UK, is developing systems that are using americium. Matter of fact, if another area of the budget that's a little bit in tenuous situation, if we still support the Rosalind Franklin mission, there is a high likelihood that we'll be able to fly one of the UK's americium roos on that mission, paving a pathway for a commercial fledgling industry here in the United States that wants to use americium. But americium and plutonium, it's not a one-for-one exchange. They don't trade the same for the missions on power, mass, thermal, radiation. And so it's not like if I say I'm going to have an americium system, I'm going to solve everything for my outer planets and I'm going to be able to close those missions. So you can't, can they be used in combination? Yes, there's a lot of opportunity. It's a both and, not an only. So we have to take that into account, but as you've heard, you actually have to have the systems. You have to have the isotope production. You have to put them in the right, the isotope in the right form. You have to clad that because you need to do this safely. And you saw the exploded fuel clads and general purpose heat source modules that Ralph showed in his slides. There's a lot of steps in there, and we're learning all of those. And so you need to get through that whole process and then develop the systems. And so that is still a long pathway. And I would submit that without the availability, the viability, and the commercial profitability, right? These americium or other alternative isotope systems won't come to be, right? And they need a strong government partnership to help us get there. So at the beginning of this conference, Dr. Kenyon asked us, what are we doing to keep America first? So for me, that answer would be simple. We're not shutting down plutonium production in the United States, because if we do, we're going to not just lose a capability, we're going to lose the future in scientific exploration. and we're going to sacrifice our leadership in the world in this area.
Well, you can tell that none of us are very passionate about this topic. We have, thanks, June. I really appreciate everything that you said and all of the panelists. We have a lot of time for questions. And so we really encourage people to questions or even suggestions from the audience. This is just the first stop on an agenda that Jim Green and I kind of put together. We really want to go to Congress with these arguments. And so you're helping us refine our talking points today by listening so carefully. So I'm going to start. If there's nobody lining up at the mics, I'm going to start. Oh, look at that.
You got me so excited.
Awesome. Yeah.
So a couple questions.
Can you introduce yourself?
Yeah, Jeff Wozniak from KBR.
Yeah.
So a couple questions to start. Do you have any white papers? We've been doing for some reason. Lots of us have been doing a lot of advocacy on the Hill. We hadn't been doing it in the past, but now we found a need to do it. Any white papers that you can share with this community so that we can take this message to Congress?
Well, I'd lie and say yes. But the fact is that there's one that's 80% done on my laptop, and I'm the long pole in the tent in getting it out.
Great.
Because we wouldn't go to Congress without a white paper.
Great.
Yeah.
And
We'll
but
save
the
our days away from that.
Yeah.
Yeah.
So we'll just get your contact.
Just a few days, and yeah, give us a card or reach out to us on LinkedIn, and we'll get it to
The
you.
president's budget for RPS goes to zero in a matter of a couple fiscal years.
Yeah.
Yeah.
W and a couple other letters.
So can I interrupt though? Also, the RPS program, the NASA RPS program that's here at Glenn, did write a number of white papers, and those are in the hands of different folks at headquarters and at the center. So you could also reach to them as well to
Maybe
get
help
those
us
papers.
out.
To make it convenient, though, I think we should try to provide them to you directly.
Sounds good.
Right.
And then the other question is, you didn't talk too much about commercial manufacture of 238. Can you talk about some of the challenges of that? Because I know that there are lots of companies that are, doing fusion products, making elements for medical devices and detection, et cetera, that are looking to go on beyond that.
So I'm gonna make a comment, and then I'm gonna see if June has a comment about this. But my attitude about the commercial production of plutonium-238 and the radioisotope power system that the product goes into is an inherently governmental function. It is something that is so complicated and so dangerous that, it's safe once the Department of Energy gets done with it, but it's not until they got it cladded and put into a GPHS, which is the brick, right? And so I would say that I hope we don't ever get to commercial production. I would want to see commercial production of the units and partnerships with NASA and the Department of Energy on how we could improve the efficiency of the entire systems. But the production of the plutonium-238 itself, I think that's an inherently governmental function.
And part of that is, of course, managing the byproducts from that.
Yes,
Storing
that's
those, making sure they're safe, safely put away, not in the environment. So there's a lot to that.
Right.
Yeah. And currently, plutonium-238 is considered a special nuclear material. And so unless it becomes a non-special nuclear material, then it really will have to have the regulation within the government to process it.
And that it's radically different than uranium that we use to power fission reactors. Plutonium-238, as soon as it's made, it starts to react, or I've forgotten the right word because I'm old, but it starts producing alpha particles, and you start getting heat immediately. Whereas with fission power reactors and the uranium that goes into that, you have to get enough of it together, and you have to remove the moderators, and that is actually a much, in my opinion, safer and probably better suited for commercial production process. Yeah.
That would go on the white paper?
I don't know if that's in the white paper or not. Well, maybe we'll add a paragraph. Yeah.
There's some of that material in the white papers that have gone into the RPS program office, and actually those have also been shared with the Planetary Society. They have copies of those as well. And I'm trying to remember, there was.
I think they have some of them. I'm not sure
They have,
this
yeah, they
complete
have
set.
some of them.
But yes.
So this has all been sort of a hurried, real time reaction to some of the things that came out with the recent president's budget request.
Planetary Society is going to the Hill next month, so this needs to be in their portfolio too.
It's really actually very rewarding to see how the community has started to come together over not just the issue with plutonium, but the entire issue of the exploration of space. And so it's I think it's fantastic that Planetary Society and the commercial industry and civil servants and retirees can all kind of come together and start like leaning on the folks in Washington that can make these decisions. So we got a question over here. Go ahead and introduce yourself.
All right. Yes, thanks. Hans Hansen, NASA Glenn Research Center's Space Science Project Office, and also Case Western Reserve alum. So a question to the panel here. So there's discussion of like dynamic conversion technologies and how that could really get more efficient systems. Any recommendations on how we can take that from the laboratory into actual demonstration and put it into mission capabilities?
I'm going to start with a confession.
Okay.
You better.
So when I was working for Jim Green, the situation with plutonium-238 was dire. And we knew that we would lose most of our programs if we didn't have radioisotope power systems. And so I began to push a new technology. Actually, it's not a new technology, a new system called the Advanced Stirling Radioisotope Generator, ASRG. And we put units on life test, and they seem to be performing pretty well. And so I took a radical move, and in the announcement of opportunity for one of the Discovery mission, there's a mission classes of about $600 million. So, I mean, it's not chump change. We said, if you design a system that needs an ASRG, we'll supply it and you don't have to pay for the power system. We'll supply the integration costs and take care of that. So it was a way of trying to force feed tech development into operational systems. That, if you've been at Glenn very long, you probably know that didn't work out so well, right? In large part because most of the people that wanted to bid on a Discovery class mission, they wanted to go deep and far into the solar system, and there was not a confidence that a mechanical device could last the 7 to 14 years necessary to do the kinds of exploration that they wanted to do, right? So my confession is I pushed it too fast, right? And so we need to keep the Stirling cycle technology under tech development. We needed to keep it for much longer. And I'm told there's still units on test today.
Yeah, I think, well, so yes, we have a number of those units that have shown long-term duration testing for over 14 years. I also think that one of the lessons we learned from that was that we had a community trying to build a spacecraft around a system that was still being developed. Mm-hmm. And so that caused definitely many conundrums. So definitely you have to understand the system before you can integrate it. The other thing is that we were pushing that system to have really high efficiency. And so making sure that you don't try to push that bar too far, too quickly would be very helpful. And then, as you said, Jim, you're looking for missions that were very, very long in duration. The RTGs, the way we did the RTGs, we didn't do it like that. They had to last months, then years. All right. The Voyagers weren't designed to last 45 years, right? So it is the fact that we need to have the right mission so that you can be successful in that, in that development and in that deployment.
Just to emphasize June's comment, so if you go back to the original requirements for the Voyagers, 4.5 years. So, the Voyagers have ended up lasting more than 10 times of the guaranteed lifetime. If that were a commercial product, well, the people that built it would be fired because nobody went back to buy another unit because these things lasted too long, right? So it's been a real, incremental thing. And there is this nervousness that, again, about the mechanics of all of this. I think at one point I looked at at least with the ASRGs, I think typically they had a vibration period of about, it was like about 80 hertz. And so if you do that for 17 years, you've got several billion oscillations. You can't go back and fix it. You can't recall it. You can't go up with a screwdriver and change something. And so, this makes people very nervous with something that's, got a few $1 billion in, in asset value. One of the things I went back and looked at, I don't know how many of you have heard of the Oxford clock or the Oxford bell, but apparently it is the longest running mechanism in the history of the world. It was put into motion. It's got a battery of composition unknown that has about they think it's about a 1 nanowatt output. It's in the basement, I believe, at Oxford University. It was put into oscillation in 1840. It has a 10-second period with a small electrical discharge that helps to move the pendulum back and forth. It's got I think it's a 10 centimeter long pendulum with a 1 centimeter diameter ball. And it has been, apparently there was a problem about 5 years ago, I think, that it stopped because of humidity issues, but it restarted itself without human intervention, and it has made a few billion oscillations. But that's the only example. I mean, we're looking at a range of doing things with dynamic systems that it's just an unknown territory, and nobody's put one of these into a thermal vac chamber for 34 years yet to guarantee the 17 years of operation. So there's a lot of nervousness about how to keep going on this.
So I see Jim wants to make a comment as well, but I just wanted to jump in and say, I don't blame the community, the science community, for wanting an MMRTG or RTG technology compared to Stirling technology, because they've had all those decades of success with a passive system. Why do I need a mechanical system, right? And June makes an excellent point, which I hadn't thought of until we sat behind this table, that we didn't get there with RTGs to 40 years in one single step. So that's a really good point. I like that.
So I think the next step for Stirling's, of course, is working with human exploration on lunar missions in terms of being able, like the Apollo, to deploy a variety of instruments that run over day and night, so to speak, on the moon, which are very long. 2 weeks of night is extremely hard. And so many things need to be deployed like that. Although we had seismometers on the moon that were using radioisotope power, plutonium-238, that were deployed, we recognized that data had severe limitations. It didn't have the number of bits necessary to make the fine observations of how the moon quakes to be able to really understand the structure of the moon. Now we have the technologies to be able to really do a great job of that, but we need a whole month cycle. We need to know the effects of the Earth and the moon, and the sun on the moon to be able to get a total seismic picture of it that allows us to get an understanding of its interior, size of its core, crust, and mantle. Recently, we have found out, based on further analysis of the lunar samples, that the moon had a magnetosphere early on when it was developed. And that means it had to have a liquid core that was running a current, and that goes against a lot of the models on how the moon is created in this giant impact hypothesis, which seems to be the leading theory. So many questions can be answered that way. Radioisotope power is going to be extremely important as we move into permanently shadowed areas and analyze the data. Now, what we need to do when we roll into those areas is core it. And the reason why, what's laying in these permanently shadowed areas are the early Earth atmosphere, the early lunar atmosphere, in addition to understanding the early comet and asteroid bombardments, which all had volatiles to it. The early Earth atmosphere comes from the lunar magnetosphere, which connects to the Earth, providing field lines for this stuff to come all the way to the moon, precipitate out, and lay in these permanently shadowed regions. We have a huge amount of new science that can be done, but in a permanently shadowed region, you're going to have to take your power, and you're going to have to be there a long time, and you may have to do a lot of coring fairly deep to be able to get access to the material you need to answer these questions.
Yeah. So Noel Hinners, who used to be the director of planetary science at NASA headquarters a long time ago, used to say that the reason we need RPSs is because 90% of the solar system is dark. And it isn't just out beyond Jupiter anymore. It's, as Jim's pointing out, permanently shadowed regions on the moon and the darkish side of Mercury. They're all places where we would need RPS. We have 5 minutes left, and I wanted to ask Jim this specific question. I'm really glad to see that we've got so many people wanting to ask questions, and we can continue to talk during the break if you like. But Jim, in 30 minutes or so, NASA's going to hold a press conference.
Yeah.
And
So at 11 o'clock.
Tell us just what you know about that. This is really exciting stuff.
Yeah, in 15 minutes. So at 11 o'clock, and it will be broadcast live here. NASA headquarters is going to announce some new findings from the Perseverance rover. Now, of course, Perseverance, which was launched in 2020, here we are 5 years later, okay, well beyond its initial mission, and in an extended mission, is continually finding some spectacular stuff. It is the mission that's coring rock, putting that in sleeves for later return. All right, this is where we get in the laboratory and really understand the mineralogy and the history of what's happening on Mars. And the reason why that's important is just basic understanding of what we have here on Earth. The Earth has well over 5,000 minerals, but about 349 of them can only be made by dead life. All right? And so consequently, as we roll into these areas where how the rock and the minerals are formed, and on that list is the potential for life to be able to be part of that mineral, and that's on the list of what it could be, we will solve that only in our laboratories. So this is an incredibly exciting discovery. As you know, because of the large expense that had been determined for how Planetary was going to do Mars sample return, the administration has said, okay, human exploration will do the sample return. And in a way that makes a lot of sense. When you think about launching something off the surface of another planet that brings back these samples, linking it to human exploration, to me, means it might be the first version of the MAV that brings astronauts home. Saturn V was created by upsizing Saturn I and going through a variety of tests. We're going to have to do that at Mars. We're going to have to land smaller vehicles, test them out, test some of the concepts of refueling, all this kind of things that has to happen before you land a MAV that will bring humans back. And oh, by the way, if you're going to launch off Mars, take some samples with you. So when we know exactly where to go to get them.
Souvenirs from Mars.
Souvenirs from Mars. So,
Right.
so it's a tremendously exciting discovery enabled only by an RPS capability.
Right. And with that, we can talk during the networking session. I'm sorry to those that there were 3 or 4 people that stood up. Happy to chat after the fact. Are we done then, Jim? All right, yeah. Okay. Thank you, everybody.
Thank you
for
very
listening.
much.
Thank you.
Hello, everyone. My name is Amrit Sitaraman. I'm currently an undergraduate student at the University of Illinois, majoring in aerospace engineering. I'm originally from Grafton, Massachusetts, and I look forward to a career in guidance, navigation, and control. As a member of liquid rocketry at the University of Illinois, I'm part of taking our mission statement and making it a reality. If you are curious about our project charter and the work that we do to get ahead in the collegiate space race, feel free to talk to any of our members. We will now take a break with snacks and beverages outside on the mezzanine. Check out the NASA tables, enjoy the networking, and build new connections. Please come back at 11:35 for our next session on artificial intelligence and space systems. Thank you.